Hello and welcome to the presentation of our work, Time for some German pre-training a transformer-based temporal tagger for German language. My name is Satya Almasian, and this is an equal contribution work with Dennis Aumiller. As motivation, I would like to point out how does temporal information fit into the context of text-to-story workshop. Temporal information is an important part of narrative style document. It is a time expression that refers to a certain point in time, a period of time, or a certain event. And it can be useful in many applications, like timeline generation, event detection, and time-sensitive summarization. Temporal tagging is usually done in two stages, extraction and normalization. Extraction refers to the detection of temporal entities in the text, and normalization is normalizing their values to a certain format. As an example of a narrative style document, we look at the Wikipedia article of Russian invasion of Ukraine. You can already see on the first paragraph, we have three different temporal entities. Two of them follow a very similar pattern, but for the third one, maybe a pattern-based method doesn't work that well. Also, for recognizing its normalized time, we have to take the context of the date into account. So the tag data is usually in TimeML format, which is an XML file that contains timex3 tags. They have two important attributes, type and value. The value refers to the normalized value, and the type refers to the type of the temporal expression that can take four different types: date, time, duration, and set. The date refers to a calendar date, time to a time of the day, and duration, as the name implies, the duration of some time, like 2 weeks, 3 weeks, or a month. Set is a time that repeats itself, like every day, annually, every month. In this work, we only focus on detection and classification of the types, and we leave normalizing values for future work. So what are the challenges in this work, and what do we actually try to address? Like many of the other tasks, the data that is available is heavily dominated by English language. Therefore, idle time, which is also from my chair, and is a rule-based system, remains the state of the art in most of the non-English languages. The problem with idle time is that it is rule-based and it is precision-focused. It is unable to generalize to unseen and unknown patterns, and if there is a slight alteration in any of the patterns, then it cannot detect the correct expression. On the other hand, neural models learn patterns and features from the data, and they do not require feature engineering. As a result, they can generalize better to unseen new rules, and they do not require handcraft data. So why are they not the state of the art as of now for all the other languages? Basically because there is not enough data to train them for a language-specific model. At the moment, the way to solve this problem is multilingual transfer learning. But it is not good as the language-specific rules that idle time creates. So we propose another method to alleviate this problem, and that is through weak supervision. We showcase this by looking at German language in particular. Weak supervision is using noisy and imperfect data to provide supervision signal for labeling large amount of training data that will be used as ground truth to train a data-hungry method, like the neural networks. We introduced two sets of weakly labeled German data sources. First one is a temp eval in German, which is already an English benchmark data, and we automatically translate it using Google Translate. A larger set is a idle time articles that contains German news articles that were crawled from the web, and idle time was used on them as a tagger. This data is used as ground truth for a pre-training stage for our classifiers. The available German data sources is only one, and that's Krauts, that contains limited number of temporally annotated news articles from Zeit and Dolomition. Let's take a look at the statistics of the data. There's a lot of numbers in this table, but what I want to draw your attention to is the distribution of Dolomition and Zeit. The Dolomitian is the train set and the site is left for the test set. Although there is 142 articles in the train set, the number of expression between the test and train is almost equal, which makes it a 50-50% test and train split. On the other hand, there is a lot of class imbalance here. The majority of the data is focused on the data expressions, and there is a few support for the other classes, which makes this very much more problematic. And the problem is that we have less support in the training set than we actually have in the test set for the real classes. For example, in the set domain, we only have 19 examples in the train set, but 39 in the test set. We hope that we can remove this problem by adding more examples to the rare instances through the idle time corpus that has 2,000 times more expressions and more instances of the rare classes. It is worth noting that the majority of the mistakes made by the multilingual model actually happens in these rare class domains. Also, by automatically translating temp eval, we were able to retain 90% of the original annotations. So how does our temporal tagging work? Temporal tagging can be thought as a special case of token classification, very much like name entity recognition. As a matter of fact, we will use the name entity schema for tagging here by using the BIO tags, O for outside, B for beginning, and I for inside of a name entity. In our case, our name entities are our temporal expression, and they contain the 4 types that were previously mentioned. To contain all of the types, we will have a total of 9 classes. As an example sentence here, 24th of February 2022 has 3 tokens, and the first one is denoted by the B date and the rest by the I date. For our token classifier, we use transformer-based language models, which are powerful token classifiers that take the context into account. During pre-training, they pick up on many linguistic cues and patterns and can achieve better results than the classic classifiers. We use G-Electra, which is a German version of Electra pre-trained on a big German corpus. I will not go into the details of the Electra model, as the language model that we use is not the focus of this study. So how does our transfer learning pipeline work? First, we have the large number of news articles. We tag them using idle time. The time ML tags are then used for pre-training our transformer tagger. Then our pre-trained G-Electra can be fine-tuned in 2 ways. Either we directly fine-tune it on the Krauss dataset and create a model, or we can do a 2-stage fine-tuning by first fine-tuning it on the translated version of the temp eval and then additionally fine-tuning it on the Krauss dataset. Now let's look at the evaluation of our results. We introduce 3 baselines. First time is naturally the rule-based teacher idle time. The second and the third one are the multilingual models. Adversarial BERT takes multilingual embeddings and align them adversarially for temporal tagging. MBERT is short for multilingual BERT, which trains a tagger only for detection but not for classification, meaning that in this case we will not have the differentiation between the temporal types. To look at different weakly labeled data and how they actually affect our models, we trained 5 different variations. The first one is just taking the G-Electra and not pre-training it, only fine-tuning it on the Dolomitian subset of the crowds, which is the training set. In the other variation, we first fine-tune it on the temp eval automatically translated data, and then fine-tune it on crowds. The third variation is our first pre-trained model that is only pre-trained on the idle time data but not fine-tuned. We include this model to look at the zero-shot capabilities. We also have the pre-trained model, same as before, once fine-tuned on crowds and once fine-tuned on the temp eval and then on crowds. The table here shows the final result of our 5 variations and our 3 baselines. Temporal tagging is evaluated using a strict and relaxed matching. Strict matching means that the exact name entity or the exact temporal expression has to be found, and in the relaxed case, if only a part of it is detected, the match is considered correct. We additionally report the type F1 scores for type classification. As you can see here, our best performing models are our pre-trained models. They improve 7% F1 score over the existing models for tagging and also 5% for the classification. It is nice to see that the zero-shot capabilities are quite good as well. They are very close to idle time, which means that we already learned a lot from idle time during pre-training. We also simulate the behavior of idle time by being precision focused in the pre-trained model, as the pre-trained models have always a slightly higher precision than recall. But idle time still remains the best precision focused model in all of it. The pre-trained models learn ultimately to balance a bit more between recall and precision. Another thing that I would like to point out is how do the pre-trained model versus non-pre-trained model handle noisy data or data from a different distribution. The temp eval data is quite noisy in comparison to our pre-training set and the Dolomitian set, because it contains probably a lot of spelling mistake, linguistic mistake, as it is just automatically translated. If we add this to the normal G-Electra without pre-training, the results are detrimental. But if we add it to the pre-trained version, it's almost so stable that it can gain some performance from it in some cases. However, this pre-training is a very costly task and requires additional annotation and also additional time for pre-training. And the models without pre-training already work quite well. So it is a question of whether you want to invest this time to get this marginal performance or not. So to conclude and summarize, we propose weak supervision for allowing transformer-based tagging into low-resource languages on a case study of German language. The pre-trained models outperform the baseline taggers in almost every metric. However, this performance doesn't come without a cost. The trade-off between the cost of pre-training and this small performance gains is something that has to be discussed. Another thing worth noting is that the language type also plays a role in this whole image. German language is very close to English, which makes the translation high quality, and also idle time was created by German people, which allows them to have a comprehensive set of rules for a specifically German language. We do not expect to have the same high quality annotations for other languages in the low resource case. For future work, we would like to extend this model to other languages and also add a normalization of temporal expression. Thank you so much for listening. If you like to download our model or look at our code base that was used for training, please refer to the URLs inside the slides.